so we'll be doing question 6.1 now. So 6.1 giving you a utility function in terms of m and s, which is equal to m times s. And part A, which is asking you to show that an increase in the price of m does not affect the quantity demanded for s. So that basically is we want to show that the change in s given the change in the price of m is equal to 0. Okay, so the change in price of m doesn't affect the quantity demanded for s. Right, in order to show this, first of all, which is how to find the demand functions for s and m. Okay, so we have a utility function, which is how to maximize the utility function in order to find the demand for s and m. So we just do like how we normally did. So the Lagrangian function will be ms plus lambda of inside the bracket it will be the budget constraint, and that which is equal to I minus i.e. the total income minus the price of m multiplied by m minus the price of s multiplied by s. Okay, so we just have to find the first order conditions where we differentiate L with respect to m. That will give us s minus lambda pm equal to 0. So that will be equivalent to s equal to lambda pm. So say this one is the first equation. Okay, so next is differential of the Lagrangian function with respect to s. That will give you m minus lambda of lambda times ps, and that equal to 0. So that will give you m equal to lambda ps, second equation. Okay, so if you differentiate the Lagrangian function with respect to lambda, that will just give you the budget constraint itself, which is I minus pm m minus ps s equal to 0, and therefore we have a budget constraint which is pm times m plus ps times s equal to I, and outside this is the third equation. Okay, so I'll try to solve for the values of s and m. So I'll take the first divided by the second. I will get s divided by m equal to pm on ps, and so therefore s will be equal to m pm on ps. Okay, so I'll substitute the values of s into my budget constraint equation, which is equation 3. I will get pm times m plus ps times s, and I already found that s equal to m times pm divided by ps, and that will have to be equal to total income. So I'll solving this equation over here, I'll get pm m plus, so ps here which is cancelled with the ps here, I'll get another m pm which is equal to I, and therefore m just equal to I divided by 2 pm. Okay, so that is the demand function for m in terms of, so as you can see from here, the quantity demanded for m only depends on the total income I and the price of m. It doesn't depend on the price of s. Okay, so knowing the amount m, very easy, you can find the amount s. So s just equal to m pm on ps, which is basically the thing we found before at the optimal condition. So by substituting the amount m into here, m equal to I divided by 2 pm times pm, and the whole thing divided by ps. So pm here cancel out with pm here, you get I divided by 2 ps. Okay, so this is the demand for s, and this is the demand for m. Okay, so we want to find the change in S given the change in the price of M. Okay, so if you are using the demand function for S, which is the thing here. Okay, so if you differentiate that demand function for S with respect to PM, you see that it equal to 0 because there isn't any PM in the equation. Okay, so part B will be very straightforward. It's asking you to show that the change in M on the change in the price of PS equal to 0, and it's very straightforward to say from, so using S equals, so using M equal to I divided by 2 PM that we already found in part A. So if you differentiate this M here with respect to PS, you see that it definitely equal to 0 because there isn't any PS in the equation. Okay, so part C, use the Slutsky equation and the symmetry of net substitution effect to show that the income effects for both part A and B are identical. Okay, so first of all, we just have to write out the Slutsky equation for M and S. Okay, so Slutsky equation for M, which is the change in the quantity demanded for M on the change in the price of S, will be equal to the change in M on the change in the price of S, such that the utility is constant minus S times the change of M on the change of I. Okay, so the first term here will be the substitution effect, and the second term here, including the negative sign, will be the income effect. Okay, so similar for the demand for S. So the change in the demand for S given the change in the price of M will be equal to the change in S on the change in the price of M, such that the utility is constant minus M multiplied by the change of S on the change of I. Again, first term is the substitution effect, and the second term, including the negative sign, is the income effect. Okay, so from part A and B, we see that, okay, so from A and B, we already obtained that the change in M on the change of PS is equal to 0, and the change in S on the change of PM is equal to 0 as well. Okay, so that basically means this equation equal to 0 and this equation equal to 0. Now the symmetry, so the symmetry of substitution, saying that the substitution effect in the first equation will be equal to the substitution effect in the second equation. So that means the change in S on the change in PM, such that utility equal to each other. Utility is constant equal to the change in M on the change in PS, such that utility is constant. So the substitution effects are equal to each other, and therefore the income effect will be equal to each other as well. Okay, so therefore negative M change in S on change in I will be equal to negative S change in M change in I. Okay. Right, so part D, it's asking you to prove part C explicitly using the Marshallian demands function for M and S. Okay. So the Marshallian demands are the thing we already found in part A. Okay, so we say from part A, the Marshallian demand for M is equal to I divided by 2 PM, and the demand for S equal to I divided by 2 PS. Okay, so that's what we found in part A already. Now using the demands function, the question asking you to prove that the incomes effects are equal to each other. Okay, so we want to prove that the change in, so the negative m change in s on change in I will be equal to the negative s change in m on change in I. Okay, so we want to prove this. So very easy to say that we will have to find the derivative of s with respect to I and the derivative of m with respect to I. So I'm gonna do that. Okay, so the derivative of s with respect to I, so I'll say this is the star equation, this is the second star equation. Okay, so by using the star first, so I'll find the change in m first. So I differentiate the m function with respect to I. I'll get 1 divided by 2pm. And if I use the second star equation, I will be able to find the differential of s with respect to the change in I, and that will just give me 1 divided by 2ps. Okay, so therefore negative m change, I should say negative s multiplied by the change in m on the change in I will be equal to negative s 2pm and negative s, sorry, negative m multiplied by the change in s on the change in I will be equal to negative m divided by 2ps. Okay, so I want to prove that this one is equal to this one. Okay, so now by using the optimal condition, so from part A, the optimal condition is where, so if I go back into here, I go back to my part A over here. Okay, this is my optimal condition. Okay, so I will be using that optimal condition in order to prove, so S will be equal to M PM on PS. Okay, so using this optimal condition, I will get that negative S divided by 2PM will be equal to negative M PM on PS and divided by 2pm, so that will give me 2pm. So pm here cancel with pm here, will give me negative m on 2ps. Okay, so I already proved that this thing here is equal to this thing here.